Thank you for connecting to this webinar about the digitalization in the Die&Mold sector through metal additive manufacturing. So the webinar is in the framework of the ADDITOOL project. It's a Interreg Sudoe project between France, Spain, and Portugal. And the project is focused on the use of metal additive manufacturing in the Die&Mold sector in order to improve the methodologies and try to boost the Die&Mold sector in Europe. In the project, there are some research centers and universities from the 3 countries, and the main idea is not to work only in the technical area of the metal additive manufacturing, but also in the diffusion and trying to give a training of the metal additive manufacturing for different companies and research centers and universities. So this webinar is in this area. So first of all, also let me introduce myself and my colleague. I'm Metal Additive from the University of the Basque Country, from the Department of Mechanical Engineering, and my colleague is Jon Iñaki Arrizubieta. He's also professor at the University of the Basque Country. And also let me thank to AFM for the support on the organization of this webinar. So thank you, John, for the technical support. And just before starting, just a final point. The ADDITOOL project will finish in February of 2023. We are having a final meeting in the 9th of February. So in the 9th of February, it will be a final meeting of the project in San Sebastian. And we hope that we have scheduled the participation of very big companies and reference companies. For example, we'll have AM Power, which is one of the most relevant consultant agencies in the area of additive manufacturing. We will have also the presence of obviously the partners of ADDITOOL project with Catec, Estia, Lortec, Zeit, Ipeleria, Enit of Tarbes. And we will have also the opportunity to have some lectures of very relevant companies like Alstom, Cranfield University, Adaxis, and also we are confirming the French company ADAP. So we invite you all to come to San Sebastian in the 9th of February to this final event. We will hope to do our best and present not only the results of the project, but also a general overview of the additive manufacturing for the Die&Mold sector and other related sectors. So once we have finished the presentation, let me start. So here you can see the content of the presentation. We will start with a very brief presentation of our research group, and also a very brief introduction of the metal additive manufacturing processes that we are researching. And then my colleague Iñaki will go on with the more technical aspects about the Die&Mold industry and the application of the metal additive manufacturing. And we will try to finish with some conclusions. And obviously, please feel free to make as many questions as you can or you have. And we will be also on the chat, so you can write your questions in the chat. So please, Iñaki. So we are from the University of the Basque Country. Our research group is the High Performance Manufacturing Group. It's research group that works in different areas. Those are the main areas: high-speed manufacturing, grinding, electro-discharge machining. Also, we have started some years ago a research line in metrology and inspection, and we are focused on the laser material processing. And mainly we work on additive manufacturing, laser welding, laser texturing. We are in the Faculty of Engineering of Bilbao, working with students. We also lecture in Bachelor Science, Master Science, also PhDs, and we develop different TRL level projects from the quite basic to transfer project, technological transfer project. We have also another workshop, which is called the CFAA, Centro de Fabricación Avanzada en Aeronáutica, probably you know it. And here we also have some additive manufacturing system. In fact, the laser powder bed fusion processes that I will talk about later is located here with two systems. And here our projects are more high tier level focused. We work mainly for companies, but also here we develop also some PhDs also. So we combine both training and research activities. So focusing on our research activities in the laser material processing, the main technologies that we are working are the powder bed fusion, the direct energy deposition, both metal additive manufacturing. Then we have also some laser texturing and also laser welding. Our main areas of research are the process modeling, monitoring, control, CAD/CAM, surface engineering. So any activities related with the manufacturing process, we try to develop these areas, and we are very focused on different sectors like aerospace, Die&Mold, automotive, and energy. So more specifically, this webinar will be located dominantly in laser direct energy deposition, which is the main technique that we have used here. And we will focus on monitoring and control and surface engineering also, and some process modeling. And obviously in ADDITOOL project, the sector is Die&Mold. So Die&Mold and some automotive. So going to the introduction now, we have focused in two metal additive manufacturing process, which are probably the main processes group used for metal. One is the powder bed fusion, and the other is the direct energy deposition. Probably you will know them, but if not, in short, the powder bed fusion is used for building parts from scratch, from zero. So the idea is go layer by layer to build a full part. The process is carried out into a inner gas chamber, usually argon. So here we have a first limitation of the process. So since we have to introduce or insert the part into a inner chamber, the part size is limited. For example, a very big machine of powder bed fusion can be 800 for 400, 500 millimeters in height, but the conventional ones typically are 300 per 300 in XY and 300, 400 millimeters. So it can be considered a relatively big system for powder bed fusions. On the other hand, we have the direct energy deposition processes. In that case, the idea is not to build the full part. So we start from a previous part, from casting or forging, and we deposit material, injecting the material onto a substrate. In that case, this process is very useful for coating a surface, even part repair. If the repair has been damaged or wear during service, we can inject material, add material in that area and repair it again, put it in order again. And also we can build some features on a part, just going layer by layer for doing a specific or manufacturing a specific feature on a local area of a big part. In that case, we do not need an inner chamber, since the inner gas is injected directly with the nozzle, with the system that inject the material. So the inert atmosphere is provided directly with the system, with the nozzle, and it gives us the opportunity of going to a very big part, so we can integrate this system in a very big machine tool or a robot. So the part can be larger, or we can go for larger part here. Okay. Going more in detail in the laser powder effusion, the idea here is go layer by layer using a metal powder. The system replace a powder layer. In that case, we use quite fine powder. The powder is relatively small. It's lower than 60 micron. We need also to fill all the plate with powder, and with an energy source, typically is a laser. The laser melts the powder that will become the part, and the melting and resolidifying of the melt pool becomes on a solid material. The process goes layer by layer, so repeating this process layer by layer in layers about from 30 to 60 microns, we can have a sequence of different layers going to the full part. The typical energy sources, as I have already told, are laser beam, and there are also some systems that use electron beam. It's not so typical in that case, but energy beam give us a little more energy and goes a little more faster using a higher grain powder. But on the other hand, the resolution of the part, the quality in terms of finishing of the part is not so good. So both techniques coexist. The process give us a very good quality part if the process conditions are well selected, and if we go in the process in the good conditions, we can obtain almost 100% dense parts, comparing with the high quality castings. And now the main applications are medical. For example, dental implants is the typical application of this process. Also, aerospace industry is going fast, introducing this technique with a lot of developments. And Die&Mold is also one of the key sectors here, since, as you probably know, these processes, the additive manufacturing is very good for complex geometries, internal cavities, so on. On the other hand, the other process, direct energy deposition, here you can see in the video, the idea is with a system, in that case a nozzle, we inject material. It can be both in powder or wire, and combination with energy source that can be a laser. We melt a substrate, previous part, and then we inject the material in the melt pool of that we have created in the substrate. So we can inject the material, deposit material in an area, and overlapping the tracks of the position of the material in a layer, we can coat a surface, and even we can go layer by layer in order to build. Here you see an example of a layer by layer sequence that we have built as a feature. Okay, In that case, the laser gives us the very good quality in terms of we have a very minimum, very small heat affected zone, and we can melt a very local area. So in that case, we have a very good resolution. And also, if the process is if the process goes with the correct conditions, with the good parameters, we can obtain a very full dense and very good quality in the deposition of the material. So just to finish that, in comparison, here you can see both techniques. On the first hand, the laser powder bed fusion, we have a relatively good accuracy, considering that it's a thermal process with metal fusion. We can obtain parts below 0.1 millimeters, so it's quite good. Surface roughness is also quite good, below 2.5 microns of mean roughness, which some people could consider that's not very good quality, but if we consider that it's a thermal process, it's relatively good. We obtain very good integrity in the parts because of the inner gas chamber. And on the other hand, we have some restrictions. For example, the building rate is not so high. We have 0.2 to 0.4 kilograms per hour, which is not so much. And on the other hand, we have the site restrictions due to the inner chamber. So if we go to very big parts, it's not affordable. And on the other hand, the laser direct energy deposition, in that case, we do not have so good quality in terms of surface finishing and tolerances. Here is very difficult to obtain tolerances below 0.5 millimeters. 1 millimeter can be the process limit. Surface roughness is also not so good. So in this case, we will need almost 100% of the times to finish with further machining or grinding operations. We also obtain very good integrity in the parts, since we also introduce protective area, protective gas. The laser is a very local heat source. We do not have a very big heat affected zone. And in this case, the building rate is relatively high, or let's say medium. It can go from half kilogram per hour up to 2 kilograms per hour in typical conditions. Even we can go further with improve in some conditions, but the typical building rate is below between this range. And we can integrate this process in a robot or in a machine tool. So the size limit is given by the system, and we can introduce the system in machine tools of several meters long range. So in that case, virtually we do not have size limit. And mainly is used for part repair or coating because of the resolution of the process. So this is just to finish the introduction. I give the floor to my colleague, to Iñaki, and we will continue with the rest of the presentation. Thank you.
Okay, thank you very much, Aitzol. In my case, I'm going to start directly talking about Die&Mold industry. As you know, this is a sector which is formed by different processes like hot stamping, metal blank sheet stamping, also forging. But in all of them, we can say like a common characteristic that a metal sheet is formed mechanically from an initial to a final shape, which is the objective of the process. And somehow we have identified some kind of typical problems in all those processes, which are the wear problems because of the friction between the blank or the part and the tool faces. Also thermal issues in case of hot stamping because of the high temperatures developed during the process, which may decrease the properties of the tools or also generate abrasion problems. Also, for the case of hot stamping, we have some kind of design limitations due to the geometry of the cooling channels, which are typically manufactured by drilling, and somehow it's restricted their shape, which is always straight. And finally, we have also identified a lack of process data directly in the forming area. Let's say that it's easy to monitor the process of the stamping press, but it's not so easy to obtain information about the blank which is being conformed during the process. We have also analyzed the actual state of the art of the Die&Mold industry, somehow what we expect from this sector in the short future. And we conclude that there won't be many changes as all the Die&Molds will continue being manufactured by casting and machining. But we have found also that there are some kind of useful applications for the metal additive manufacturing that they can make a difference in the process. First of all, we need to highlight that the manufacturing process of a die it's rather long. It starts from the design process. Afterwards, we have to cast the material. Afterwards, machine, and that process can take a couple of years. Therefore, during that process, any geometrical change of the tools, of the design of the car, can change also the shape of the active faces of the tools. And therefore, in case that that modification implies adding material, we will have a huge problems in terms of cost, time. So the additive manufacturing can add these geometrical details and save a lot of time and money to the industry. Also, the critical areas that suffer a lot of wear problems could be repaired by additive manufacturing. Also, any error during the machining process, like a tool that breaks during the milling process or a wrong program trajectory, all those errors could be corrected by the additive manufacturing. And finally, during the adjustment process, which is usually done by hand manually, and material is being removed, somehow instead of removing material, if it's required to add material, the additive manufacturing could solve these problems. So once that we have identified the possible applications of the additive manufacturing for the metal industry, we have focused in 4 cases, which is the part repair, the thermal enhancement, the sensitization of the tools, and the surface properties modification. And in the next slides, we are going to show you a couple of examples of these applications in which we have worked at the ADDITOOL project. The first of them, which is the part repair, at this point, we can distinguish different opportunities. On the one hand, the most logical one is that the metal additive manufacturing can repair a damaged or a worn surface, and therefore we can extend the lifespan of the components, and somehow this helps when achieving the sustainable development goals. On the other hand, also, we can manufacture what is called like the material tool. Instead of building the whole stamping tool with the same good steel, good, I mean hard, expensive, we can combine 2 steels, one which is cheap, also easy to machine for the bulk, and after that we can deposit a layer on its surface to increase the properties and ensure the proper working of the tool. And also the final opportunity or the possibility offered by the metal IM is the last moment geometry modification about what I have already told you before. Okay, so in order to give one example for the part repair, this is a case study that we have manufactured with inside the ADDITOOL project. This is like a clamping device in which we have to position a stamp part, and we will use it to check whether the stamping process has been properly manufactured. Traditionally, this part was built in 15 CDV6, which is aeronautical steel, quite expensive and not so easy to manufacture and work with it. And instead of doing it that way, we have tried a new strategy, which is building the base in IC 1045, which is a common steel, rather cheap, easy to manufacture. Then we eliminate 1 millimeter material in the active surfaces and we fill it with the good 15 CDV6 material. Here in this video, you can see how is the deposition process. First of all, we deposit the outer clad, and afterwards, line by line, we fill all the inner geometry. Okay, as I has told you before, in order to obtain a layer, and then layer by layer, we deposit the whole height, which in the present case consisted of 3 layers. On the image of the right, you can see the final shape of the repair tool. One of the main benefits of this strategy is that the final machining process only consists of some small areas, which simplifies this process, the machining one, and also lowers the tool wear that suffers. The second application is related with the surface properties modification. Traditionally, when we thought about the additive manufacturing process, we will always think of the filler material, which in the present case is powder shape. We introduce this material in the powder feeder. In our case, it's a gravimetric powder feeder. We introduce inside, it falls down thanks to the gravity. We have a rotatory plate, and controlling the velocity of rotation, we control the feed rate of the powder that comes from this pipe to the nozzle, and we inject it into the melt pool in order to obtain a clad made with the material A. However, in the metal additive manufacturing, we can combine different materials in order to obtain what is called a metal matrix composite. In this case, we add simultaneously 2 materials, and the clad consists of a combination of both materials. Moreover, we can control the feed rate of both of them and the ratio we are feeding, and we can build what is called a functionally graded material, and we can control the chemical composition of the clad, and we can vary that chemical composition in every clad or every layer. In order to show you an example of this metal matrix composite, here I can show you a couple of pictures of an Stellite 6 and tungsten carbide deposition. The Stellite 6 is a cobalt-based hard-resistant alloy. In this case, we have performed the test in the CFAA, which is the High Performance Center that I has told you before. We build small sheet parts and we analyze them. First of all, we perform an integrity verification. And as you may see in this picture, we have the Stellite matrix, which is metallic matrix, and the discrete tungsten carbide. This is ceramic particles embedded or introduced inside the clad. In this case, this test was performed using the FGM strategy because we vary the composition of each layer. First of all, we start adding only Stellite 6. Then we introduce also 5% tungsten carbide, 10%, and in the last layer, we can go up to a 50% tungsten carbide and obviously 85% of Stellite 6. That way, we avoid crack problems and we increase the resistance of the coating. Also, as we have a metal matrix composite, we perform an evaluation between the bonding of the tungsten carbide particles and the metal matrix. And as you can see in the right figure, there is like a small diffusion layer, but it's so small that doesn't affect the properties of the Stellite 6 matrix. And also this diffusion layer ensures the proper bonding between the tungsten carbide and the metal matrix. So once that we have ensured the integrity of the clad, we have analyzed the performance, both mechanically through the three-point bending test, and also the wear performance of this clad. And as you can see in this figure, increasing the tungsten carbide percentage implies higher resistance to the wear problems, which is really interesting, for example, in the tool and die industry. The third example that we are going to analyze is the thermal enhancement. In this case, if we want to manufacture hot stamping tool steel, we need also to manufacture via drilling the cooling channels, which are always straight shaped. And this implies that the distance between the active phase, which is the inner line here, and the coolant channel is not constant, and we will have some kind of hot spots where the heat is not extracted, as well as in the areas where the drilling hole is close to the surface. So in this case, thanks to the additive manufacturing process, we can manufacture a cooling channel which is always at a constant distance from the surface. We eliminate the hot spots we have talked about before, and also we can obtain a faster cooling cycle. In order to show this feature, I'm going to share with you the results of thermal simulations which we ran with the software ANSYS. The first case corresponds to the stride drills, and we analyzed the behavior of the tools and also the cooling cycle of the metal sheet which is being stamped. As you can see, there are some kind of hot spots where the heat extraction is lower than the rest of the blank. And we designed new cooling channel systems based on the additive manufacturing process capabilities, and we are going to analyze the differences between the straight drilled and the conformal cooling channels. For this purpose, we designed the upper and lower tools, also the blank geometry. We performed the meshing tool in order to remesh the element size in the area close to the contact regions and the cooling channels. We introduced the boundary conditions, and here we can differentiate two operations. First of all, the stamping and quenching operation, in which we have a hot blank in contact with the tools and we are extracting heat through the convection. And in the second stage is the one corresponding to the loading and unloading operation of the blanks. In order to obtain a stable regime, we perform 30 consecutive stamping operations. And here you can see the results where we can compare the results for the case of the strike cooling and the conventional cooling. And thanks to the metal additive manufacturing strategies, we can save up to 15% in the cycle time. And the final application corresponds to the sensitization of the tools. As I have already introduced previously, extracting information from the inside the die-and-molds when they are closed is quite complex, mainly because when we introduce a thermocouple, for example, we are going to affect also to the thermal behavior of the tools. But also obtaining this information is necessary in order to digitalize the manufacturing process. And we think that the additive manufacturing process is one of the key factors in order to achieve these objectives. In order to show the capabilities of the metal additive manufacturing, we are going to show you some results we obtained in a parallel project to ADDITOOL, which is SUSI. It's a project financed by the Basque government. And in this case, we introduced a thermocouple inside a hot stamping tool. Here, the main difficulty relies on the fact that we are adding material on the shed of the thermocouple, which is really thin. in the cases we used, we performed like a benchmark of the different diameters of the thermocouples, and we were able to embed even up to a 3 millimeter diameter thermocouple, and that implies a 0.3 thickness coating on its surface. So here you can see the results we obtained, and we conclude that in order to add material over the thermocouple, but without damaging the sensor, we need to lower the laser powers even up to a 50% when compared when we are adding on the flat surface. And also, in order to stabilize the process, because heat dissipation in the thermocouple is rather small, we need to include cooling time between the different clad deposition. Luckily, we can also use the same thermocouple for monitoring the process. And as you can see in this video, while we are depositing material on the thermocouple, we measure the temperature, and somehow we obtain two benefits. On the one hand, we can control the cooling time, so we know when to start when depositing the next line. And on the other hand, if we damage the thermocouple, we will also notice that on the temperature measurement. The thermocouple was embedded. We analyze its performance by touching directly with the hand, and as you can see in the video, the response of the thermocouple was really fast when heating, and also when the hand releases, it captures really fast the cooling process. And also the mechanical properties of the laser additive manufactured materials are ensured because we deposited the ICH13, which is a hot stamping tool steel. So in order to sum up with this presentation, I'm going to briefly introduce you all the conclusions we obtained. First of all, thanks to the metal additive manufacturing, we can repair worn or damaged dies so that we increase the lifespan of these components. Also, we can manufacture bimetallic stamping tools thanks to the coating of cheaper materials, which results in a cost reduction. Also, thanks to the free-form manufacturing capabilities of the additive manufacturing, we can obtain conformal cooling channels and reduce the cycle time. Also, thanks to the capability of the additive manufacturing to combine different materials, we can manufacture metal matrix composites, so we improve the wear properties and also the hardness of the tools. And combined with this fourth conclusion, we can also say that thanks to the functionally created material, we can develop new materials and also combine materials that originally were not compatible. And finally, we have successfully embedded a sensor in a hot stamping tool, so we can improve the Die&Mold monitoring systems. And with this, we finish the presentation for today. Thank you for your assistance, and if you have any questions about what we have talked today, please feel free to write in the chat or ask directly through your microphone. Thank you.
First of all, thank you, Iñaki. And
Okay.
Any question? Yes, Eneko?
Yeah, we have a question here in the chat asking if the presentation will be available on the website. I think yeah, the answer is yes. It will be available on the website. Yeah.
Okay. Just to remember the invitation to the final meeting in the 9th of February. So we encourage you, if you are interested on additive manufacturing, to come to San Sebastian. And in the chat, you have the link for the registration. And if as you can see, the the meeting will be an event, not only for the project, for the ADDITOOL project, but also we will have the opportunity to see huge companies and very high impact companies. So just to remember. Yes?
I have a question on the chat asking about the stability of the powder stream while making a different material combination. Okay, maybe you can answer this.
Okay, I can answer it, and Iñaki, please feel free to interrupt me.
Yeah, of course.
So it's a very good questions, because here, as you see, we combine very different materials. For example, the density of the stellite 6 and the tungsten carbide is very different. So also the aerodynamic of the powder is different. So we expect that both materials do not behave, or do not have the same behavior in the nozzle and in the gas stream. So we have performed some analysis using computer fluid dynamics of the nozzle, and we have seen that they do not have the same focal point. There is some difference in the focal point of the powder, but we can set the changing the values of the gas stream and changing the parameters of the laser and adapting the melt pool. We can obtain a relatively good mixing of the powder. But yes, this is one of the key points of mixing materials. The stability, not the stability, but trying to have the same behavior of the both materials in the nozzle. In terms of stability, we have to say that the mass flow is quite stable in the case of our powder feeder.
I think you have answered perfectly. In the experimental test that we have performed, we did not realize any stability problems when depositing one material or two materials. And the only thing to take into account is what ADDITOOL has already explained, that the proportion of both materials in the powder feeder and in the deposition plane at the nozzle itself is not the same. So based on the simulation and experimental results, we need to adapt the ratio between both powders in order to obtain the composition that we want in the clad.
We have another question about how much. No, sorry, I'm going to answer this on the chat, but maybe it's more interesting for discussion the challenges of these new technologies, considering requirements like hardening, and so what you see this technology is going to be in the future. Maybe. Right. So I don't know if I translate clearly the question, but literally says the question: what are the process challenges as far as the manufacturing of items like drill bits, considering a requirement like hardening, etc.?
I'm not able to understand what does it mean, drill bits. Sorry,
I would say it's brocas, no?
Yeah, drill brocas, but drill bits, punta de broca, I don't know. But
what in Cosana maybe asking is that we are not able to manufacture, that's exactly the circular drills. Somehow the lower face could be circular, but in order to deposit material and close the cooling channels, we need to deposit some kind of 45-degree walls until we finish closing the cooling channel. So it's like a bridge that we have to close layer by layer. So we need to use the 5 axis.
in any case, continuing with the challenge, hard materials, for example, tool steels are always challenging because they have a very crack tendency because of the weldability. So in general terms, one of the big challenge of the laser material deposition or laser direct energy deposition is trying to solve all the problems of low weldability materials. And in that case, we can introduce preheating, we can introduce different strategies, but this is probably one of the main challenges.
Yeah, that's it. Somehow, when we have to work with a new material, we take as a reference the advices for welding processes of that material, which usually imply preheating up to extremely high temperatures. And thanks to the lower heat input of the metal additive manufacturing, in our case, the laser directed energy deposition process, we try to reduce the preheating temperatures. Sometimes we are able to deposit the material even at room temperatures. For the case of the H13, in other materials like the ADDITOOL tool steel, we are not able to do that at room temperature, and we need a preheating and also post-heating heat treatments. So it's quite tricky, to be honest. Yeah, what Inigo Terrero asked, we haven't coated the internal cavities. We know that there are some nozzles for depositing material at the internal cavities, but it's quite for big internal cavities. So in our case, the cooling channels, they are like 6 to 8 millimeters in diameter. So it's not possible to introduce a nozzle inside the cavities. Okay, so answering to Juan Isasa, it was a trial and error methodology. So we took different diameter thermocouples, and we start with the conventional temperature, and we went lowering until we are not able to melt even the shed of the thermocouple. So afterwards, we analyzed the cross sections of the thermocouples, and we visually analyzed if we are melting enough in order to ensure the good adhesion between the filler material and the thermocouple or not, or what happens. And the tool, and of course, if we change the thermocouple, for example, there are some of them built with Inconel 718, others of AC316. If we change the material, we will also have to characterize again the additive manufacturing process parameters, but also that happens when depositing material on any material, on any base. I mean, the process is material dependent, geometry dependent, and laser dependent. Yeah, thank you, Juan, for the question.
Okay, so thank you for all. I thank you to
the AFM.
To FAM for the organization, the technical organization of the meeting. Thank you also to Stia for coordinating the project, the tool project, and I hope that the information that we have told you now have been useful for you. And in any case, feel free to contact us. So thank you.